Picture the solar system as a well-lit room. Comets and asteroids come through the door all the time, familiar guests with familiar habits. They follow the pull of the sun, they grow tails when they heat up, and their paths can usually be predicted with cold, satisfying math. Then 3I Atlas arrived, and the math still worked, but the story started to feel 3I Atlas is an interstellar comet, a visitor that formed around another star and is now passing through our neighborhood only once. That alone is rare, only the third confirmed interstellar object ever observed, after 1I Oumuamua and 2I Borisov. But what makes 3I Atlas worth a closer look is not just where it came from, it is how it behaves once it is here. Astronomers track its position night after night and compare that motion to what gravity alone should produce. The differences are subtle, measured in tiny changes that matter only because the predictions are so precise. There is also the comet itself, the way its activity turns on and evolves, the way its dust and gas appear from a distance, and the occasional odd feature that makes researchers pause and run the numbers again. So here is the question that will guide this documentary. When an object from another star system does not fit perfectly into our categories, are we seeing a rare but natural comet, or a clue that our models are missing something? Over the next minutes, we will follow the discovery, the measurements, and the competing explanations. Not to chase a fantasy, but to practice something harder, staying curious while staying honest. Late in 2025, researchers even pointed the Green Bank telescope at 3I Atlas to search for narrowband radio signals, a basic sanity check for anything truly strange. They reported no signal from the comet, but the check itself shows scientific caution in practice. The story of 3I Atlas begins the way many modern discoveries begin, not with a lone astronomer at an eyepiece, but with software chewing through a flood of images. Wide-field survey telescopes take repeated snapshots of the sky, then algorithms look for points of light that shift position from frame to frame. On July 1, 2025, one of those surveys, the NASA-funded Atlas system, flagged a faint moving object. At first, it was just another candidate among many. But when follow-up observations came in, the orbit fit started to misbehave in a very particular way. Most solar system bodies travel on closed paths. They are bound to the sun, meaning they will come around again. 3I Atlas did not. Its trajectory was hyperbolic, an open curve that says, this object is passing through and will not return. That single geometric detail carries a huge implication. If it is not bound to the sun, then it did not form here. It came from interstellar space. Calling it the third interstellar object is not hype, it is bookkeeping. The first, 1I Oumuamua, appeared in 2017 and sparked debate because its acceleration looked odd. The second, 2I Borisov, arrived in 2019 and behaved more like a familiar comet. 3I Atlas became the third entry in a very short list, which is why every measurement matters. Once the interstellar nature was clear, observatories around the world pivoted. NASA notes that multiple space telescopes were tasked to study the comet, including Hubble, Webb, and SPHEREx. The goal was simple: gather as much data as possible before geometry and sunlight make it hard to see. Timing shaped everything. After discovery, the comet remained observable for a while, then moved too close to the sun in the sky to track easily, and later reappeared for renewed observations in early December 2025. Its closest approach to Earth came on December 19, 2025, still far away in human terms, but close enough for precise tracking and deep observations. That window of attention is what turned a dot of light into a scientific event. Because every interstellar visitor is a sample from another star system, a physical message in a bottle. And with 3I Atlas, the early data hinted that the message might be harder to decode than expected. During those first days, teams refined the orbit with each new observation. Tiny errors in position become big differences when you extrapolate weeks or months into the future. As the fit tightened, the conclusion stayed stubborn. The comet's speed and curvature could not be explained by a recent planetary slingshot. It had arrived with its own momentum, earned somewhere else, from an ordinary natural body or not. Interest also spilled beyond normal comet science. On December 18, 2025, the Breakthrough Listen program used the 100-meter Green Bank telescope to scan 3I Atlas across a wide radio band, looking for artificial narrowband signals. None were found that traced back to the comet, but the observation added another layer to the public conversation and raised the standard for what counts as evidence. By the time the discovery adrenaline fades, science becomes a grind of measurements. For 3I Atlas, that meant using every wavelength we can manage, because different wavelengths reveal different physics. Start with the simplest tool, astrometry, repeated position measurements against background stars. Plot enough points and you get an orbit. With an interstellar object, the orbit is the story, because it tells you how gravity is shaping the motion and whether anything else is pushing. Small bodies can experience non-gravitational acceleration, a gentle extra shove caused by jets of gas and dust as sunlight warms ices on the surface. Comets do this all the time. The surprise is not that a comet can accelerate. The surprise is when the acceleration does not line up cleanly with what we can see. Now add photometry, measuring brightness over time. If a comet's brightness changes in a repeating pattern, that often means the nucleus is rotating, presenting different surface areas toward us. In late 2025, detailed observations showed evolving activity, including jet structures associated with a rare sun-facing feature sometimes called an antitail. Researchers reported a wobbling pattern in those jets and used it to infer a rotation cycle on the order of hours, suggesting a complex spinning body rather than a smooth, uniform ice ball. Then there is spectroscopy, the technique that spreads light into its component colors like a fingerprint. In comets, spectral signatures can reveal common volatiles such as water, carbon monoxide, or carbon dioxide, and can hint at dust composition. For 3I Atlas, NASA describes it as an active comet with a coma, a cloud of gas and dust produced as solar heating drives sublimation. That is the standard comet mechanism, and it places 3I Atlas in the natural category by default. But standard does not mean simple. Even for well-behaved comets, the relationship between outgassing and acceleration is messy. A jet can be narrow, intermittent, or pointed in a direction that is hard to resolve from Earth. And because 3I Atlas is small and far, many of the most important physical quantities must be inferred rather than directly imaged. NASA's fact sheet reflects that uncertainty in the size estimates. Using Hubble observations from August 2025, astronomers constrained the nucleus diameter to a range from roughly 440 meters up to about 5.6 kilometers. That is a huge span, but it is honest, because brightness, reflectivity, and dust all tangled together in the measurement. Spacecraft added more angles. NASA notes a close pass by Mars on October 3, 2025, when spacecraft there might catch a glimpse, and later other missions obtained observations as well. The SETI Institute described Europa Clipper capturing ultraviolet imagery of 3I Atlas in November 2025 from a vast distance, showing that even missions built for other targets can contribute data when a rare visitor shows up. So what are the main puzzles once you put all of that together? First, the object is interstellar, which already makes it unfamiliar. Second, its activity evolves in ways that are not identical to the two previous interstellar visitors. Third, some observers point to small discrepancies in motion and morphology that are difficult to pin down because the measurements are hard at these distances. And that leads to the core scientific tension. We can explain many of these features with ordinary comet physics, jets, rotation, dust, geometry, and sunlight. But we cannot yet explain them with certainty because we do not have a close-up view. When you are missing the close-up, every inference becomes a question. Are we looking at an unusually configured comet nucleus shaped by an alien star system, or are we seeing something that forces a new category entirely? The radio search adds one more data point: no artificial emission, yet it cannot prove absence. Once you have data, you have a choice. You can treat every oddity as noise and move on, or you can ask, what set of explanations can account for all of it without cheating? That is where theories come in, not guesses but structured stories that make testable predictions. The first class of explanations is natural, and it is the default for good reason. 3I Atlas is described by NASA as an active comet with a nucleus that releases gas and dust to form a coma when warmed by sunlight. In this view, most of the apparent weirdness is a familiar mix of rotation, uneven jets, and viewing geometry. A small jet can act like a thruster, producing subtle changes in acceleration. A sun-facing dust feature can appear as an antitail depending on how the dust sheet aligns with our line of sight. Natural models also have a deeper appeal. Interstellar objects are expected to be strange because they are not samples from our solar system. They formed in different chemical environments, were blasted by cosmic rays for long times, and may have been heated, fractured, or coated in ways we rarely see at home. If 3I Atlas looks unusual, that might be exactly what you should expect from an object that has traveled between stars. But natural does not mean solved. The hard part is that several key properties are poorly constrained. We do not know the nucleus size precisely. We do not know how active regions are distributed across its surface. We do not know the internal structure, whether it is a monolith, a rubble pile, or something in between. With those uncertainties, it is possible to explain almost anything after the fact, which is not satisfying science. That dissatisfaction is one reason a second class of ideas appears, the artificial hypothesis. This is the claim, in its strongest form, that the object could be a probe, debris, or technology from an extraterrestrial civilization. Avi Loeb has argued publicly that interstellar visitors are worth checking for technosignatures, not because we should expect a spacecraft, but because the stakes are high and the cost of looking is low. The same attitude shows up in the Green Bank observations by Breakthrough Listen. They scanned 3i Atlas across radio frequencies and reported no artificial narrowband signal associated with the comet. That result does not prove the object is natural, but it does remove one popular kind of evidence people imagine, a beacon or a transmitter. Outside the peer-reviewed literature, a parallel conversation grew. Media coverage highlighted a CIA response to a public records request that neither confirmed nor denied the existence of records about 3i Atlas, a standard legal posture that some readers interpreted as secrecy. That is not scientific evidence, but it does influence public attention, and it is part of the ecosystem around any unusual sky event. So where does that leave us? Natural explanations are strong and consistent with NASA's classification, but details remain uncertain. Artificial explanations are logically possible but currently unsupported by direct evidence, and the best targeted radio search so far found nothing. And that is the uncomfortable, useful conclusion. Both stories leave open questions. If it is a comet, why does it look this way, rotate this way, and evolve this way? If it is not a comet, what new evidence would we need to say so without fooling ourselves? In science, mystery is not permission to believe anything. It is an invitation to sharpen the test. A good theory also tells you how it could be wrong. An artificial origin would need control, course corrections, or power output unrelated to sunlight. A natural origin would need jets, dust, and timing that match physics. Even as debate churns, the comet keeps moving, and future geometry will decide what we can learn next. The key milestone on the outbound leg is the passage near Jupiter in March 2026. NASA's own tracking notes that 3i Atlas will venture past Jupiter on its way out of the solar system. Why does Jupiter matter? Because Jupiter is the heavyweight. Its gravity is strong enough to reshape orbits, perturb dust, and amplify small differences in trajectory into measurable outcomes. If you want to test whether motion is purely gravitational plus ordinary outgassing, a close encounter with Jupiter gives you a powerful lever. During the flyby window, researchers will watch three things. First, the orbit. Small deviations from prediction can be quantified. If the trajectory follows the expected curve within uncertainties, that supports the simplest model. If it deviates in a structured way, especially after accounting for jet activity, the mystery deepens. Second, the comet's activity. A change in sunlight angle, rotation state, or tidal stress could alter jets or dust production. If the anti-tail and jet features evolve in ways consistent with known comet physics, that points toward natural mechanisms. If they behave in ways that are hard to reconcile with heating and rotation, then new modeling will be required. Third, the radio and multi-wavelength watch. Even after a non-detection, teams may repeat targeted searches because the situation changes as distance and background interference change. The goal is not to chase aliens. The goal is to reduce uncertainty and close loopholes that speculation feeds on. There is a psychological reason this flyby matters too. Interstellar objects are rare, so every one becomes a test of how we handle ambiguity. Do we rush to declare it normal, or rush to declare it impossible? Or do we do the harder thing, wait for better data? March 2026 is not a finale, it is a checkpoint. If 3i Atlas behaves exactly as predicted, we will still have learned about comet physics beyond our solar system. If it surprises us again, we will have a clearer reason why. Expect coordinated observing campaigns, ground telescopes, space telescopes, and opportunistic spacecraft data, all stitched into one timeline. NASA has already described how the comet became hard to observe near the sun and then reappeared for renewed observations, so teams know the rhythm of visibility and gaps. Jupiter is one of the last gravitational landmarks before the comet fades into the dark between stars, beyond the reach of cameras. By now, 3i Atlas should feel less like a headline and more like what it really is, a traveling experiment. It is a physical object from another star system, crossing our solar system on an unbound path and giving us a short, precious window to measure it. We started with the Discovery, a survey telescope in July 2025 catching a faint moving point, and orbit calculations revealing a hyperbolic visitor. We followed the data, from optical tracking to spectra and evolving cometary activity, including unusual jet structures that helped infer rotation. We noted what NASA emphasizes, that this is an active comet with a coma, and that multiple space telescopes were brought in to study it. Then we entered the swampy part, interpretation. Natural explanations fit much of what we see, but leave uncertainties because key properties are hard to pin down. Artificial explanations have captured attention in public discourse, and scientists have responded the right way by testing for signals. The most sensitive radio search so far found no artificial emission associated with 3I Atlas. Next comes the Jupiter passage in March 2026, a chance to watch how this object behaves under the pull of the solar system's biggest planet. That flyby will not magically answer everything, but it can tighten the orbit, refine models of outgassing, and narrow the space where mystery can hide. So here is the final question to sit with. When the universe hands us a rare sample from elsewhere, do we use it to confirm what we already believe, or to stretch our understanding until it fits the facts? 3I Atlas will leave. The better test is what we do while it is still here. And if more interstellar objects arrive, and they will as surveys improve, each one will be a page in the same book. The mystery is not a monster, it is a method.